An angle is something formed when two straight lines meet. So it's a concept I'm sure we're all extremely familiar with, and really what I want to do is to talk about how we can numerically describe angles, or measure them if you want. So, for example, if I take a straight line here, and another straight line meeting it here, an angle is, well, this, right? This is an angle. And I'm going to represent it with the Greek letter theta, is often how we might do it. I'm going to do that all the way through this video. Okay, another example would be, I don't know, similar, something like this. So this is an angle as well. So it's some sort of geometric concept which describes the way in which two lines meet each other. Of course, you could do it slightly differently as well, so it's just worth pointing out. If I have something like this, we could talk about not the angle, the smaller of the two, we could talk about the angle around the outside if you want this. It's perfectly valid as well. Okay, so an angle is it's a geometric idea, right? It's a concept, or it's something that turns up when I have two straight lines intersecting each other. Or two rays, in a sense, if you want to put it that way. When I say a ray, it's like saying you have a start point and then it's kind of going out infinitely in some direction. Okay, so we want to describe these numerically. So we want to somehow talk about them extremely precisely, using numbers. Now, there are two ways to do this, which are used frequently in mathematics. The first is the one that you learn first, which is the concept of degrees. So degrees are kind of the more elementary, in a sense, of the two. But what we're going to find is that they're going to be simple, but kind of arbitrary. So they're not going to be terribly natural. They're going to require some sort of arbitrary choice. So they're kind of simple, but ultimately, arbitrary. The other way we're going to do it is using something called radians. And this is going to seem a little bit more complicated, but it is much more natural. So it's more natural in the sense that it doesn't involve really arbitrary choices in the same way. And ultimately, especially for calculus, it's significantly more useful. Degrees are very crude. They're useful if you're doing pretty crude calculations. I mean, people use them all the time. But if you're doing really precise mathematics, radians are infinitely superior, as you're going to discover. So this is kind of a more natural way to describe an angle. More natural and ultimately more useful. Although in this course you're not really going to see why it's so much more useful. You have to do calculus to really see why radians are much better than degrees. So these are going to be two different ways to describe angles numerically. Okay, so an angle is a very geometric thing. How do I associate a number to an angle in a sensible manner? So let's do degrees first, shall we? So degrees is a very simple idea. You basically are going to take, the full circle, if you want, and you're going to divide it into equal segments, small equal segments. And you're going to divide the circle into exactly 360 equal pieces. That's basically the plan with degrees. So let's kind of separate into two cases as always. Okay, so let me just show you the basic idea. I think it's much easier to see this. Here we go. So that's the basic the basic setup for degrees. So you, as I said, take the entire circle and subdivide it, if you want, into 360 equal pieces. So subdivide is just a fancy word for divide. Divide the circle into 360 equal segments. So a segment of a circle is like something you cut out, like a piece of a cake. And these equal segments are going to be called single degree segments. Single degrees. So a single sliver will be 1 degree, that's what we're going to call it. So there are several things about this that are useful, in the sense that 360 is extremely divisible, right, by lots of low numbers. And I think there's no single definitive reason that 360 was chosen. There are probably a lot of historical factors that go into it. I always look this up whenever I teach this, and I don't think there is a definitive answer about 360 as the number. But it's a sensible number because it's divisible by so much. It's divisible by 2, 3, 4, 5, 6. Is it divisible by 7? I need to think about that one. Doesn't matter. Divisible by all sorts of things, right? 10. Lots of things, right? So basically, we have this system where we're going to divide the circle into these pieces. And when we talk about an angle in degrees, we're going to talk about it very simply. When I talk about the angle in degrees, when I say theta, and I describe it in degrees, it's just going to be the number of single degree segments required to make the angle up. So this is going to be the number of single degree segments required to make the angle. Required to make theta. It's that simple. So if theta was 1 in degrees, the angle would be very, very thin. It would be a single degree segment. If it was 180, then it would be, well, 180 is half of 360. It would be a straight line, basically. It would be 2 rays facing out from each other. If it was 90, well, I should maybe draw these in, it might be simpler. So if I have this as my 0 position, if it was 90, it would be that, which we often call a right angle. So lots of very familiar angles here in degrees. So let's make sure this is kind of labeled. Okay, so what have we got? Let's just do some pretty simple examples. So just quickly, examples. Examples of theta is equal to 90 degrees. Well, this is what we call a right angle. Theta, a right angle, just as I drew a moment ago. And if something is 90 degrees, so let me just do it one more time. As I'm sure you're familiar, we describe what's going on there. So this is 90 degrees. When you write something that's 90 degrees, you write it with kind of a little square there to represent the fact it's a right angle. Often called perpendicular. A really fancy word for it is orthogonal, but that's not going to be something to worry about until further in the course, well, further in other courses. So if the angle is less than 90 degrees, so let's go back to this, and that would correspond to the internal angle given by these kind of rays like this. So for example, if it was there, so if my angle was this, then we call this an acute angle. Kind of because the point is sharp. I think that's the best way to put it. So this is just straightforward terminology that you're hopefully familiar with. It should be just reminding you of it. Theta and acute. And I suppose if we are strictly bigger than 90... Oh, and I should say, I've never mentioned this, when you write something in degrees, to indicate that it's in degrees, you write this kind of degree symbol up here. So that's just to indicate you're describing an angle in the degree measure, if you want. Again, I'd hope you're familiar with that. So this is if and only if theta is obtuse. So we've got a right angle, acute angle, obtuse angle. So just up here, obtuse is where you have something kind of like this. It's that kind of business there. Not hugely important for what we're doing, but it's something that you should certainly be aware of. So as I said, this is a pretty useful thing to do because it's divisible by lots of different things. It's divisible by lots of different things. It's not divisible by 7, because 350 is divisible by 7. And unfortunately, we're 10 away, and 10 isn't divisible by 7. So I was losing my mind before. But it's divisible by a lot of different stuff, right? So it's really good. Now, 360, as I said, was chosen for murky historical reasons, but it's divisible by so much it's quite useful when you're dividing the circle up into kind of a reasonable integer number of pieces. But it's arbitrary. Right, 360 is a completely arbitrary number when it comes down to it. We could choose anything. We could choose 1,000. We could choose the number which is 2 times 3 times 5 times 7, just all the prime numbers, for example, for up until a certain point. We could have done that, something that would be very divisible by lots of small numbers. So it's a bit murky. 360 is a middle ground between too big and too small. So too small being not enough things dividing it, so it wouldn't be terribly useful. But again, it's arbitrary. So radians is a much more natural way to do it when it comes down to it. So let me attempt to do this really neatly. So if I take a circle, same basic story. So maybe what I should do is the following. I want to make this as accurate as possible, so I want to know exactly where the center of the circle is, just so I can show you this properly. So let's take a circle. And let's draw out here. Now if I take a circle, and let's take an angle in the circle. So let's do the following. I shouldn't erase that. So let's take some angle. I'll make it acute just to make it reasonably obvious what's going on. And imagine this is my angle theta. So this is my angle theta. Now I need to come up with a numerical way to describe this angle. So what I'm going to do is the following. I'm going to take the length here, this length, and that of course is the radius. That's the distance from the center of the circle to the edge, straight line distance. And I'm also going to look at the length around this segment. So maybe what I should do is kind of cut this off just to really highlight this fact. So I'm going to cut this off as best I can. Okay. So let me just zoom in a bit to make sure this isn't a total mess. Okay, that's pretty reasonable. So what do we have? Well, we've got this segment, and let's label the length around the edge L, shall we? L. So this is a circular segment given by the angle theta. Kind of just like the ones we saw for degrees. Kind of like the ones we saw for degrees. But I'm not dividing the circle into anything at all. I'm just taking my angle theta and thinking, how can I assign a number to it? So first of all, this L is called something that's called the arc length. Kind of the length around the outside. And of course, as I said before, this R is the radius. Now, is there some way I can describe this angle which is natural? So first of all, this is something kind of subtle, but if I take this segment, I could take many different radii. I could take circles of all sorts of different sizes. So if I was to take, let's say, the number L as my description, or some sort of numerical description for theta, that wouldn't make sense because different circles would have different L's. However, if I was to take any two segments, let's say, any two segments, so let me kind of get another one, which had the same angle, any two segments which had the same angle, like this. So these would be called, I suppose, similar segments in the fact that they're kind of similar. The only difference is the scale is different. So as I said, if I took the length around the outside here, and the kind of the radius here, I'll call this R sub 1 and L sub 1. L1 is different than L, obviously, but something very beautiful is true. It doesn't matter what the size is, the ratio of these two things is always the same. So what is always true is L, so kind of a nice fact here. So fact, L divided by R is equal to L1 divided by R1. So the ratio of these two lengths is always the same. And these guys are similar segments, if you want to put them like that. They've got the same angle. Similar segments. So what does this mean? Well, because of the fact this ratio doesn't care about the size of the segment, it's pretty sensible to define that as my numerical description of the angle. Remember, I'm trying to associate a number to theta, and I want to do it in a kind of a reasonable way. So here's what we're going to do. We're going to take this observation, this fact, and use it. So theta in radians, I'm going to define this to be this ratio, the arc length divided by the radius. And by this fact, it doesn't matter how big my circle segment is. Right? The ratio is always the same. Sure, the arc length could be different and the radius could be different, but the ratio is the same. So this is a really cool idea because it's getting at something natural in this procedure. Right? There's something less arbitrary about it. We're not having to make some sort of arbitrary choice like fix one specific circle and then do this, or break the circle up into a specific number of pieces. This is a really kind of sensible, elegant way to describe the angle using a number. So there is a special case which is very useful for this. So here's an important one that we should definitely be aware of. So an important special case. What would happen if I chose the circle of radius 1? So the circle of radius 1. Well, if r was equal to 1, this would imply that theta in radians is equal just to the arc length. So that gives you a really nice concrete way to think about this. If you're dealing with a circle of radius 1, the radian measure of the angle is just the length around the outside, the arc length of the circle. So when we talk about a circle of radius 1, we call it a unit circle. We've talked about this a bit before. So the unit circle. So the unit circle is just a circle with radius 1. And this, when I'm writing this, I'm thinking of, well, this is me describing theta in radians. So really what I'm saying is theta in radians is the arc length, because dividing by 1 just leaves it the same. Arc length around the unit circle. Nice. Okay, well, we need to know arc lengths around unit circles. What's the formula for the circumference of a circle? It's 2 pi r. So for a unit circle, the entire length around circumference, the circumference of the unit circle will be 2 pi times 1, which is just 2 pi. So what does this tell us? Well, if the full length around the outside is 2 pi, it should be fairly easy to talk about things like right angles, that kind of thing. So let's take a circle where I've labeled the lengths of the unit, of the arc length. So this is going to look kind of similar to the degrees, but it will be very different in terms of where it comes from. So let's take a circle. Let's take this guy. So what have I got to? So I've got this circle. So what am I basically saying? Well, I'm saying this is a unit. It's a unit circle. So it's 1 around here. So the radius is 1. And what is going on here is, if I take, for example, the full length, let me try and draw this, the full length, this is very badly drawn, will it snap to correct it? No. If I take the full length, that's not too bad, is it? If I take the full length of the circumference in the entire circle, that's 2 pi. So for example, if I wanted to describe something which was 1/8 of a full circle, what would I need? Well, I would take this segment here, as you can see, and I would need the length around this. That's what I would need. So what would that be? Well, if I'm choosing 1/8 of a full circle, the length, the arc length would be, it would be 1/8 of a full, which is 1/8 of 2 pi, so that would be pi over 4. If I wanted a right angle, well, same story, but then for the right angle, you'd be going up to here. So really what you'd want is this length around the edge. Sorry for my bad drawing, but it's that length you'd want. So what's that length? Well, that would be 1/4 or 2/8 of a full revolution. Full revolution is 2 pi. 1/4 of 2 pi is pi over 2. So that red line had length pi over 2. So when I'm talking about a right angle, it would be pi over 2. And I'm using the circle of radius 1, as I said, because the ratio is just the arc length around the outside, so it's much simpler. Here, simplify things, this ends up being 3 pi over 4. Here, of course, 1/2 of 2 pi, which is pi. Then this guy would be equal to 5 pi over 4. All nice and simple. This turns out to be 3 pi over 2. This would be 7 pi over 4. So this is me marking in some kind of core, angles that you'd be familiar with, or it's good to be familiar with. So as I said, just to reiterate, what we're doing here is just taking the arc length around, and that, because it's a unit circle, is the angle in radians. So this, for example, is arc length pi over 4. So it's just length pi over 4. Okay. So the only real difference when it comes down to it is what a full revolution is, what a whole circle is as a number when it comes down to it. So giving the number 360 for a full circle is kind of useful but arbitrary. Giving a full circle in radians is 2 pi, which actually is much more natural, as you're going to see when you study calculus. But it's the same kind of picture. You've got a full circle, a number associated to it, and you divide the circle into pieces accordingly. And we're not really dividing the circle into pieces for radians, but we're looking at the length around the outside, which is a really nice idea. So, observation. So it's important that we can go between these two ways of measuring angles. And if I want to understand what proportion of a whole circle an angle is, I can do it fairly painlessly in either situation. So the fraction of a whole circle given by theta, some angle. So as an example, e.g., it would be a quarter of a whole circle if theta is a right angle. Well, in degrees, what would it be? Well, it would be the number of degrees divided by a full circle. So it would be theta in degrees divided by 360. And if it was in radians, it would be theta in radians, whatever that number is, divided by a full circle. Well, that's 2 pi, isn't it? Because the circumference of a unit circle is 2 pi. So what does that mean? Well, I can take this and I could solve it for theta in degrees or theta in radians, which is going to give me a way of converting between degrees and radians, which is important. So, conclusion. Here's the conversions between degrees and radians. Conversion between degrees and radians. So I don't think this is something you should memorize particularly. It's something that you should understand. So you should understand that basically you're using this formula to get what I'm about to do. So if I have something in degrees, how could I get something in radians? Well, imagine if I had, let me just put this up here because it's important. If I had this here, so if I know what this is, and I'm looking for this, what would I do? I would cross multiply by 2 pi. So that would be what? It would be taking it in degrees and multiplying it by 2 pi and dividing by 360. So that means the conversion to go to radians would be multiplication by 2 pi divided by 360. So you basically look at what proportion of a whole circle it is in degrees, that's dividing by 360, and then multiply it by 2 pi to scale it into radians. And of course, to go back, you divide through by that, but that's just multiplying by the reciprocal. So if I want to go from radians to degrees, I would multiply by, well, the other way around. You see, if I had the radians now and I wanted degrees, I would need to cross multiply by 360 to get the degrees. So that means I should multiply by 360 divided by 2 pi. So that's me dividing by 2 pi first, really, to work out what proportion of a whole circle it is, and then multiplying by 360 to convert to degrees. So very important, something you should most definitely understand. Let's do some important examples. Ones that you kind of want at your fingertips. So first of all, 360 degrees clearly corresponds to 2 pi in radians. So one side is degrees, kind of obviously from the notation of the degree notation. Here we're thinking about this side in radians. 180. So a half revolution is just equal to, well, it's a half of 2 pi, which is pi. We've already seen this. 90 degrees. $90 degrees is equal to what? It's equal to pi over 2. 45 degrees, another important one. Pi over 4. Now a bit more interesting, 60 degrees. Well, 60 degrees is 1/6 of a full circle. So it'd be 1/6 times 2 pi, which is pi over 3. But if you want to do it really carefully using this conversion, it would be what? It would be 60 multiplied by 2 pi over 360. It would be the top. It would be going from degrees to radians. Finally, I mean, this one's easy as well because we know what 60 is. 60 is pi over 3. 30 degrees must be half of that, which is pi over 6. Now, something to be aware of here is these angles all involve pi, right? And very frequently, you see pi when you're writing these in radians, so note. While it's common to see kind of pi in radian notation, in radian measure of an angle, I'll write it like that. It's definitely not necessary, it doesn't need to be there. So just as an example, I mean, so if I took the circular segment, so let me kind of attempt to do this quickly. Do a bit better than that. So if I took the circular segment given by this basically, so let me just zoom in and cut some oh no. So forgive me, I just want this to be reasonably neat. So if I take this circular segment, and let's assume that let's assume the radius is equal to the arc length. That's perfectly possible, isn't it? So we could have the radius here as equal to the arc length. That's a totally reasonable possibility. What would that mean? That would mean this angle here is just 1 in radians, because it would be r divided by r. All right? So the reason pi turns up frequently really is because the angles you look at overwhelmingly are fractional parts of a whole circle. And if a whole circle is 2 pi, if I'm taking a fractional part of it, it's going to be a fraction times 2 pi, so it's going to naturally involve pi. But that's not necessary at all. Absolutely not. So don't think that radians always have to have a pi in them, right? They don't always have to look like a fraction times pi. That's only when you're taking a fractional part of a circle. So just to recap, when describing angles, we have 2 basic ways of doing it. One is degrees. We break up a full circle into 360 equal segments and then just count how many of those we need to make up my angle. That's pretty useful because 360 is divisible by lots of things, but it's very arbitrary. Then we have radians, which is a little bit more difficult to begin with, but actually much more natural in the sense that if I take my angle, theta, and I draw a segment with internal angle theta like this, I observe, well, it doesn't matter how big my segment is, the ratio of the arc length to the radius is always the same. So because it's always the same, it's sensible to use that. That's kind of a natural number associated to the angle. So we decree that the angle in radians is the ratio of those two. So the arc length to the radius. Then we observe, to make this more concrete, if you were doing with a unit circle, so if r is equal to 1, then the radians would just be the arc length, because it would be the arc length divided by 1. So that's pretty useful, right? It gives us a really concrete way of thinking about what radians mean when we're thinking about the unit circle, so the circle of radius 1. And finally, the conversion between radians and degrees is pretty natural. We just observe that a full circle is given by 360 degrees, or 2 pi radians. So we know if I take any angle and I work out what proportion of a whole circle it gives, it's easy to do that in 2 ways, by taking in degrees and dividing by 360, or taking in radians and dividing by 2 pi. And using that formula, we have a really nice way of switching between the two. And it's nice to have these kind of very, very familiar to you, so that when you're doing things in radians, these are kind of right, or immediately at your fingertips.